Okay. Good afternoon. And we're back again. Lecture 6 online. So what we're going to move to really for the rest of the semester is a much more quantitative section of the course. So we'll start looking at air pollution modeling. We'll first look at what we refer to as box models, then we'll do Gaussian dispersion models, and then we'll look at air pollution control technologies. So just a couple of reminders. Semester project is posted. There is an interim report due April 6th. You should be working with your groups. Hopefully you have contacted your group members. There's a list on Kappa, so please do that. And then the other thing is that the meteorology homework is due on Monday. There are 3 computational problems that are all based on the work that we did the other day, so make sure you take a look at those. We'll have extra office hours or office hours on Monday, again from 2 to 3:30. So if you have questions, happy to answer your questions. If you have questions before that, just email me and hopefully you'll figure out a time that we can touch base. The other thing is lectures are now posted both on YouTube and I'm posting on D2L. I don't know how much disk quota I'll have on D2L, but for now, I'm posting in both locations, and the links to the YouTube videos are on Kappa. So let's look at air pollution concentration models. So what we're attempting to do here is what we want to be able to do is we want to be able to predict the concentrations of high pollutants. So if we have a stack, as we mentioned, we've looked at meteorology. So we have these pollutants. Here's our stack. Here's our person. And maybe we have a tree here. We want to be able to determine what impact that pollutant may have on that tree, on that person, etc. So we're looking at predicting concentrations of pollutants. We want to be able to quantify how much emissions. We're also very concerned with the meteorological conditions that dictate how those pollutants will move. And ideally, we want to be able to do this with total confidence. So we want, ideally, a perfect model. Unfortunately, there are no perfect models. It's one saying that all models are wrong, some are useful. None of them are perfect, and none of them predict exactly where these pollutants will be and exactly what their concentrations are. But we still can use these models, and we'll talk about some of these uses a little bit more. But basically what we're looking at is we want to be able to predict, for instance, with an initial permitting application, what might we expect in terms of concentrations downwind. All of these are based on mass balance principles. So whether we use a Gaussian model or a FIC, what we refer to as a fixed box model, they're all based on mass balance. The fixed box models are relatively simple, relatively easy to use. We can use those if we have multiple point sources. We can use them if we have area sources. And we can also use them if we have both conservative or reactive pollutants. Now, the approach that we're going to use here is essentially the same approach that we used with indoor air pollution. It's a little bit different aspects in terms of the notation that is conventionally used. So for instance, with indoor air pollution, we used the air changes per hour. Typically, we don't use air changes per hour for these box models, but instead we will use the velocity, because what do we typically measure? You look online, okay, I want to look at what the weather is. I'm going to look up what the wind speed is. So what these models do is we're going to assume that we have some sort of a rectangular box. This height here is our mixing height. So we've talked about the mixing height. We've showed how to determine the mixing height. So that H is our mixing height. We're looking at wind entering along the width. So this is our width here. You can see it along here. And the wind enters along this face of our box. We'll assume that we have uniform concentration. So we're going to assume that we have a well-mixed system, if this would allow me to do this. Okay, so we have a well-mixed system. So the concentration at any point in the box is the same. Also, as we've discussed before, if that is the case, then the concentration in my box is the same as the concentration leaving my box. Now we're also assuming that this wind speed is independent of elevation. It's constant and it doesn't depend on the location. So if I were to measure the wind speed along anywhere along this face, it would be the same. We know that's an approximation. We know, however, that's the assumption we're going to make. We will also assume, and we'll use the term B we used before, we used Cn or C ambient, is what we used when we talked about indoor air quality. The notation here is that's used is often B. So that's the concentration entering this face. We also talked about a source term before, so S. In notation that's typically used here is Q, and we have a Q that is both a mass per time, and we have Q sub S that is mass per area per time. And the area that we're going to use is the width and the length. So we're looking there, I'm going to change color. So there what we're looking at is we're looking at this area here. So we're looking at the base then of the model. So this corresponds to the red hatched area. On the other hand, going back here, this U, we're looking at the black hashed area along that face. Does that make sense? Question, because this is important. So we can move forward. The other thing we are going to assume is then, let's go back to this model here, and now we'll pick another color here. we're going to look at this face right here. Okay. All of the pollutant that leaves is going to leave from that face. So there's no pollutant leaving out of the top. There's no pollutant leaving out of the sides. It simply moves in from the one face here and moves out to the other. Okay. And then the last thing we will assume is that we can use first order kinetics. So again, we just have the change in concentration with respect to time is equal to, if we have decay, it's a negative. If we were to look, so this is decay. If we have formation, then it would be positive. That's okay. So here we have formation. And in all cases, we're looking at a first order reaction. So just as we developed a mass balance for indoor air quality, we're going to do the same approach for developing a mass balance for this fixed model. So in all cases, what we have is we're looking at the rate of change, so the change in mass with respect to time, and that is equal to the mass leaving, mass entering minus the mass leaving. And if we have a reaction term, let's draw that in here, then we have the mass rate reacting. And sorry about that. The mass rate reacting. Okay. So what are we assuming? So our mass is equal. So we have mass is equal to concentration times volume, same as previously in the semester. This volume is equal to our length times our width times the height. And if this is constant, then I can remove that. It's now a constant, it's outside of my differential, and what I have is I then have my length, width, height, dc dt is equal to, this is a source term, what is entering through the face, what's leaving out the opposite face, and what is reacting. So here, if it is reacting and we're losing chemical, then it's going to be negative. So that's loss. And if we have formation, then it's positive. So we can actually write this expression with either formation or loss of the pollutant I'm looking at. So what I've done is I've developed a series of equations for you. So we have both I'll give you both the non-steady and the steady state. So notice here, okay, this is the non-steady state form with first order decay. Note here, if you have decay, then this term is actually positive. If you have formation, then it's negative. And that's because the terms actually switch. Think of this, if it's both decay, then these terms need to add together. And that's the same in here. Okay, so with all of these terms here. It's essentially the same equation. If you go back and you look at the equations that we used for indoor air quality, it is essentially the same equation. Okay. Notation was different, but it's essentially the same equation. So for instance, this U over L term, and why does this not write sometimes? This was equivalent to I when we looked at indoor air. So if you go back and you look at these equations are essentially the same. Notation's different, but it's essentially the same equation. And then this term here corresponds to that initial state. I've written the equation both in terms of Q and in terms of a specific Q. So remember this Q sub S. We go back here. Okay. So Q sub S and Q sub A are related here. So all I've done is I've given you both sets of equations. This is just the non-steady state equation for a conservative. So notice there's no Q in this, there's no K. So in this case, K is equal to 0, so the K term drops out. This initial term simplifies, and we have this equation. If we have a steady state solution, then all the exponential terms drop out, and we have a much simpler solution here. And finally, in this case, the initial concentration is 0. There's no contaminant flowing into this cell, so we have this equation. So what we're going to do today is we're going to spend some time mostly doing some problems and looking at how do we approach these problems. So what I'm going to ask you to do where you are is start to write down some of this information. Okay, it'll make it easier, and I think it'll help when you're trying to follow through on the computational homework problems. So what do we have? We have a valley, and I'm going to switch. Okay, so we have a valley that is 4 kilometers in width, 18 kilometers in length, and we have a concentration entering the valley of 1.1 milligram per cubic meter. We have an inversion layer hanging over the town, so we have a height of 130 meters, and we have wind at 1/2 the mixing height blowing at 1.5 meters per second. So that's the velocity we'll use. The degradation of methane in the atmosphere can be described by first-order kinetics, and we have a rate constant of 7.25 times 10 to the minus 4 inverse hours. And this is an area where we have a significant amount of hydraulic fracturing or fracking wells. We have 1,420 of them. Parts of Pennsylvania would look like this. And each of them are emitting methane at a rate of 2.5 grams per second. We also have some confined feeding operations, and each CAFO has an average of 1,500 cattle, and each cattle is emitting methane at a rate of 12.2 grams per hour. So all that is actually pretty consistent. That's typical emission rates, both for a fracking well and for a cow. So the first thing that I want you to do, okay, and is let's draw this diagram. Okay, so what do we have? So we've got a box model. I'm going to draw it the same way that I drew the other one. So here's my box. My width is always in the perpendicular to the wind direction. So here's my wind. We said it was 5.1 meters per second. Okay. The length, so the wind blows along that length, and that is 18 kilometers. This is 4 kilometers. The height is 130 meters. We have a concentration of methane entering the cell at 1.1 milligram per cubic meter. We don't know what C out is. And we have several fracking wells that are emitting methane. And I'm not very good at drawing cows. Here's my cow, there's a towel. And we have lots of cows. So we have several farms, and that cow is also emitting methane. And we can draw, and I'm going to change the color so we can draw our system boundary. So we're looking at methane in, we're looking at methane out of the cell. And this would be our cell. We are also, let's just, we have K equals to 0.0000725 inverse hours, and that is 2.014. We need all our units to be consistent. That's 10 to the minus 2.0 times 10 to the minus 7 inverse seconds. S well is 1,420 wells, each emitting 2.5 grams per second. So we have 3,550 grams per second being emitted. And from the CAFOs, we have 3 CAFOs, each has 1,500 cows, 12.2 grams per hour, and 60 minutes per hour, and 60 seconds per minute. And that is 15.25 grams per second. So we have about 15 grams per second from all of the CAFOs and about 3.5 kilograms per second from the fracking wells. So the next thing we want to do is develop a general mass balance. So what I'm looking for when I ask you to do that really is thinking about what what are our source terms? Okay. So we have the mass rate in from through the wall or the face of the cell. We have our mass rate from the CAFOs. We have our mass rate from the wells. We have our mass out through the opposite face, and we have the mass out to the reaction. And we can write this, well, if we assume the volume equals a constant, so I'm just going to write that down because that's one assumption we can make. And then this becomes volume dc dt. And then the mass in is my wind speed times my concentration times my width times my height plus the mass rate of the CAFO that I calculated plus the mass rate of the wells minus u, because we're going to assume the wind speed leaving is the same as the wind speed entering. So I'm just going to write u equals u in equals u out. So the wind speed doesn't change. It's the same in the cell and leaving the cell. Times my concentration times WH, and then minus K, C, and remember we always used V, so we'll use W, H, and L. So I've just written in terms of each of those terms. So we've assumed volume is constant. Wind speed is constant, and it's constant across the cell. It's also constant in time and space. So it's constant both in time and space. We'll assume that our emissions the emission rate is constant. We're going to assume, let's assume all the wells are operating. We're going to assume it's a well mixed system so that C in the cell equals C out. And we're going to assume that my mixing height is constant over the time studied. So basically my inversion layer isn't lifting. Any other assumptions we should add here? Thoughts on assumptions? Okay. So the next thing I'm asking you to do is to determine the steady state concentration. So if I have steady state conditions, that means that the change in mass with respect to time is equal to, and here's where I wait for the answer, but I will just write it, 0. Okay. And then we have that equation that we just used. So that is equal to 5.1 meters per second, so our wind speed times the concentration, and I'm going to put everything in grams. Remember, this was in milligrams, so I've just converted it to grams per cubic meter. I need to convert all of my distances to meters. So now meters cubed, I've got meters, 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 and meters cubed that cancel, and I have units of grams per second for source. Plus 15.25 grams per second, that's for my CAFO, plus 3,550 grams per second from my wells, minus C times 5.1 meters per second times 4,000 meters per 1 cubic. Sorry, 4,000 meters times 130 meters. So that was my width and my height. And then lastly, minus 2.014 times 10 to the minus 7 inverse seconds times C times 4,000 meters times 1,800 meters times 130 meters. And I can solve for C, and C is equal to 2.4 times 10 to the minus 3 grams per meter cubed, or 2.4 milligrams per meter cubed. Okay. So that would be, under these operating conditions, with all of the wells operating, with all of the cattle in this cell, this would be, I would end up with, at steady state conditions, a concentration of 2.4 milligrams per liter. So it's increased from 1.1 from the previous, from the adjacent cell. So if we go back here, remember this was 1.1, and now what is leaving is 2.4 milligrams per cubic meter. So that's the concentration leaving. Now, what would happen if all of the hydraulic fracking wells suddenly ceased operation? So we've got a condition here. We're going to start. We've achieved steady state conditions. Okay. So this is what we start with. For whatever reason, all of the hydraulic fracking wells stop. So we have no wells. We still have the source term for the CAFA. Okay. So now, okay, this is that Q. We can go back to, let's look at equations. Okay, what do we have here? Okay, we have, it's not the right one we want. Let's see. Okay, so we have a non-steady state solution. And we have first order decay. We have a C naught term, and we have a B term. So this is the equation we're going to use. So we're going to use so this is now the equation that we will need to use. So we go back. Here. Okay, so what we want to know is what is the concentration we're looking at, sorry. So what, look, we want the concentration 2 days after this operation ceases. So we have 15.25 grams per second. We're going to divide that by the volume. Plus 1.1 times 10 to the minus 3 grams per cubic meter. That was the B term, times 5.1 meters per second. So it's U divided by L. We're going to divide that by 5.1 meters per second over 1,800 meters. Again, that's U over L plus K. We're going to multiply that by 1 minus e to the minus 5.1 meters per second over 1800 meters. Again, that's at u divided by L plus my rate constant. I need to multiply that by 2 days. This is in inverse seconds. So we need to multiply by 86,400 seconds per day, plus that last C sub naught term, and that's e to the minus, and this is exactly the same thing here, 5.1 meters per second over 1800 meters, plus 2.014 times 10 to the minus 7 times 2 days, times 86,400 seconds per day. And lo and behold, we finally do the math, and we actually end up with 1.1 times 10 to the minus 3 grams per cubic meter, or 1.1 milligrams per cubic meter. So the moral of the story is, in this case, under these conditions, in this size cell, the CAFOs actually don't have any significant contribution to the concentration of methane. It's entirely the wells that were contributing to that concentration. And it's not surprising, really. The wells, the source from the wells was 3,500, roughly 3,500 grams per second, but only 15 from the CAFOs. Questions about that problem? Yes, no? Okay, let's do one more, and then we'll call it a day. But let's take a look at this one. And if you have any questions, feel free to unmute you should be able to unmute yourself. Feel free to do so and ask, but barring no questions, we'll move on to the next example. So in this case, we have a similar situation. We have an area source. Okay. And in this case, there's going to be cars. So what do we have? We have a width of the box of 15 kilometers. We have a length of 80 kilometers. And we have a thermal inversion, and it's limiting mixing to a depth of 15 meters. We have wind that's blowing clean air. So in this case, B is equal to 0. And between the hours of 4 and 6 p.m., we have 250,000 vehicles on the road. And in that 2-hour time span, they each drive a distance of 40 kilometers, and they're emitting 4 grams of carbon monoxide for each kilometer driven. Okay. So let's just, before we move on, let's just quick calculate Q sub S. So what do we have? So Q sub S, we have 2,500 cars. Each car is driving 40 kilometers, and each car is emitting 4 grams of carbon monoxide per kilometer driven. In this case, what we're going to do when we calculate Q sub S, we're calculating it per area of the base of my cell. So it's the width times the length. So we have a width. I'm just going to convert this to meters. And a length of 80,000 meters. And we need a time factor. This is over this 2-hour time period. And there's 3,600 seconds per hour. So that is equal to 4.6 times 10 to the minus 6 grams per meter squared per second. So notice in this case, it's not grams per second, but it's grams per meter squared second. And what you're asked to do is to estimate the concentration of carbon monoxide at 6 p.m., assuming that there's no carbon monoxide in the air. So C naught is equal to 0, K is equal to 0, and we also said that B is equal to 0. And we want the concentration at 2 hours later. So we start at 4 p.m. So we're starting at 4. We're asked what is the concentration at 6 p.m. So again, here's my box model. I have wind in this direction. It is 0.5 meters per second. The height we said was 15 meters. The length was 80 kilometers. And the width is 15 kilometers. Okay, so that's the conditions we're looking at. And we're going to assume that mixing is instantaneous and complete. So the equation that we can use for this, and these are just from the equations that I gave you before, is CT is equal to Q sub S L over UH 1 minus E to the minus U over LT. And you should be able to go back and look at the most general form and be able to derive this equation. And this is 4.6 times 10 to the minus 6 grams of carbon monoxide per second per meter, I've got the meter squared, per meter squared, times the length, which is 80,000 meters, divided by 0.5 meters per second is our wind speed, times the height, which in this case is 15 meters, and that is equal to 2 milligrams per cubic meter. So that would be the concentration in this cell that I've defined with 250,000 of cars on the road driving within those 2 hours. We're assuming that it's constant within the 2 hours. Okay, so just thinking back too, we haven't mentioned so we said it was 40 kilometers. That's per 2 hours. So we're assuming that they're driving the whole 2 hours, okay? Or on average, they're driving the whole 2 hours. Same sets of assumptions that we had before. in terms of the constant mixing height, constant volume, etc. And if you just kind of give standard, the 1 hour standard for carbon monoxide is 35 parts per million, which is about 40 milligrams per cubic meter at 25 degrees C and 1 atmosphere. So this is well below the 1 hour standard for carbon monoxide. So any questions about what we've done so far? My advice is take a look at you've got the meteorology homework, but if you have time over the next few days, take a look at the homework. You do have one problem where basically what it is you've got a series of cells, and I'm just going to draw them separately just to make it a little easier to think about. So there is one problem like this. Sorry. Okay. And basically you have air coming in here. So you've got B, and I'm going to call that B1. And then you've got C1 leaving. That is going to become B2. And then you have C2 here, that it becomes B3, and then you have C3. So basically what you have is you have a series of cells, so an area that you've divided up into 3 cells, and you're looking at each of them sequentially. So in order to solve that problem, you'll need to divide up that problem to, as I said, 3 different cells and solve it that way. Any other questions? I will add a participation question this afternoon. The participation question is going to be just to state one challenge that you've experienced over the last week and one success. If you don't want to tell me that, you can always tell me just anything. You still get the participation points. But what I'm trying to get you to do is think about kind of what successes did we achieve over this last week. It's a very different time, but hopefully, maybe they're minor, but hopefully we've all achieved some successes over this last week. So we'll end there since I don't have any questions. And I will meet with all of you on Monday then. And if you, as I mentioned, if you have questions on doing the homework, just let me know and we can arrange a time to meet.
Professor?
Yes?
I've actually had a question about that car problem.
Yeah.
So you wrote out like the CT equals QSL over the UH, and then like what happened with that E term though?
Okay, the E term here.
Yeah.
You're right, I didn't write it out. I'm sorry, thank you. 1 minus E to the minus, thank you for doing that, mentioning, I just lost the page. So this would become U, what was it, 0.5 meters per second over, sorry, it's 80,000, losing meters, times the time, which would be the 2 hours, and I have to multiply by 3,600 seconds per hour. So thank you for realizing that I somehow left off that E term, and it does need to be there. So appreciate that.
Thank you.
Any other questions? Okay, I will, as I mentioned, I will post the notes from this. I will also the written notes, and I will also post the video on YouTube and on D2L. I apologize for giving you both. Times are strange. So until Monday, have a great weekend.